right. Hi, class. This is very strange because I'm going to record this class for you. And you will be watching it. So this is the first time I've done this. So I want to get your opinion and see what you think, because I really was hoping to do this for 6-1, because 6-1 has a lot of opportunities where I wanted you to do the work and then come back and see if you did it correctly, because it takes a lot of practice. And sometimes we don't have enough time in class to do that. So I thought that if you could watch it on your own, and because some people work faster than others, I figured if you watched it on your own, I would give an example of an exercise, and then I would say, okay, now you try this one. And then you could pause the YouTube video, work on it, and then watch my solution to see if you got the same thing. That was kind of my idea for 6-1, and that's one of the reasons that I wanted to try doing this video today for 5-5 and just the start of 6-1. And you can let me know what you think. Maybe I'll put out a Google form and say, what did you think of the video? And I guess what I want you to be thinking of going through is, did you find that you had a bunch of questions that weren't being answered that maybe you would have asked during class? Stuff like that. Like, did you feel like I addressed the questions that you had? Basically. So anyway, so let's try this for this week and see. I don't want to do it all the time. It was mostly just me wanting to do this today because of 6-1, which would be coming up on Wednesday. 6-1 is pretty time intensive. And then next week, going back to synchronous classes. It seemed like you guys were pretty split when I asked you the question on the survey of whether you liked synchronous or asynchronous. So we'll try this just for this particular topic. All right, so last time we left off talking about systems of equations and inequalities. Last time we graphed two inequalities. They were both linear. We talked about the difference between whether we have an equal to in the inequality or we don't have one. If you don't have the equal to symbol in your inequality, you're going to use a dashed line. And if you do have the equal to sign, you're going to use a solid line. We also talked about two different ways of graphing our linear equations. The first way, for this particular one, we talked about using intercepts to find the y-intercept, let x equal 0, and vice versa. And then we graph the intercepts, and you just need 2 points to graph a line. And then for the other linear inequality, we solved for y. And you can tell that this one was a little bit easier to solve for y because you didn't have a coefficient in front of y. For that one, you had a coefficient of 2. So for this one, we solved for y and then graphed our inequality. And remember, we're always using a test point here to determine the solution set for the inequality. So which region will be shaded. And we're just shading the region that, in our case, did or didn't contain 0, 0, depending on the test point. So over here, we tested the point 0, 0. And we saw that it did not make the inequality true, so we did not shade the region that included 0, 0. We shaded the other half of the graph. Same idea with this one. We tried it with 0, 0. We used the test point. We found that it didn't make the inequality true, so we didn't shade the region that included 0, 0. We shaded the other region. The other type of linear equation that you're going to see this with is just either a vertical or a horizontal line. In this case, we have x is less than 2. That is the equation or the inequality representing a vertical line. Remember, the vertical line is of the form x equals, a horizontal line is of the form y equals. So a vertical line for x equals 2, remember we usually start out thinking about graphing these with an equal sign. Is just the vertical line that goes through 2. And since this is strictly less than, I'm going to use a dashed line. Make sure it's not solid because you don't have that equal to. Now, if you want to use a test point here, that's fine. You absolutely can use a test point. But sometimes students see this very intuitively. They say, okay, well, if x must be less than 2, then I need to be shading anything less than 2. If you see that intuitively, great, do that. If you want to use a test point, that's fine. You can also use a test point. And again, 0, 0 is a good point to test because it's clearly on one side of the graph versus the other. So if you were to test 0, 0, well, x being 0, you're asking yourself, is 0 less than 2? Yes. So you're going to shade the region that includes the point 0, 0, which is this one. And that's how you would graph this inequality. Now, using that same idea, for number 2, you're being asked to graph the inequality y is greater than or equal to the log of x plus 5. Now, if you don't remember your log graph, that's okay. You should have a good idea of what it looks like. Remember that the log of x plus 5 in parentheses means that your graph is being shifted to the left 5 units because that addition is happening inside the function. So when you're graphing and you're shifting to the left 5 units, you're looking for the log function that does that. If you don't remember what your log function looks like, feel free to graph it in your calculator. I'll pop mine on here. It's daylight. It should show up. It does. And then you can graph your log function. Log x plus 5. And then I'm going to zoom standard here. Okay, and you can see the graph that's being shifted to the left 5 units. Now it looks a little bit different than the one that you see on the paper. Notice how the scaling is different. However, this one is the one that matches the graph that you're seeing on the calculator. And if you want to really make it match, you can always change the window to have an x minimum value of -20 and an x max of +20. And a y minimum of -5 and a y maximum of +5. And then you can graph it again. And there's that graph. It is clearly B. This one right here looks like it would be log of x -5. But this is the graph that matches. And check the inequality. This one is a little bit easier to just eyeball. You're talking about values of y that are greater than or equal to this log function. Well, the only values of y that would have to fit that description would be the ones that are above. The greater than or equal means above. And I think it's easier to see that when you have y by itself. So we're going to use that a little bit more talking about these inequalities. But y is greater than or equal to the log function means it has to be y values that are above there. And if you're not sure, you could always pop in a test value. Maybe you could test something like 0, 1. I'm looking at this function and I'm noticing on the graph that the point 0, 1 is clearly in the shaded region. And we can double check to make sure that that makes the equation true. You're asking yourself, is 1 greater than or equal to the log of 0 plus 5? Oh, sorry, you got to see that. And then you can check. Log of 5 is 0.6989-ish. Yes. So the 0.01 does make this inequality true. Hence, that is the solution to the inequality. This is your solution set. Okay. Now we're going to talk a little bit about circles. We talked a little bit about circles last time, and we talked about how you can graph a circle in your calculator by splitting it up into 2 functions. One of them is the top of the circle, the other is the bottom of the circle. You've probably talked about the equation for a circle before. Maybe it's been a while. I'll remind you now. The definition of a circle is the set of all points in a plane that are equidistant from a fixed point called the center. The fixed distance from the circle center to any point on the circle is called the radius. So you're thinking about your circle, you've got this center point, and then the radius is just this halfway point between the middle of the center of your circle and then any point on the edge of your circle represents the radius. Don't get it confused with diameter. The diameter is just the distance all the way from one end of the circle to the other. So here's your radius. And then if you were to go all the way through the circle, that would be your diameter. So that's the difference there. Remember, the circumference is the distance around a circle. Sometimes we get all these things mixed up. The standard form of the equation of a circle with center HK and radius R is x minus h quantity squared plus y minus k quantity squared equals r squared. This has to be a plus sign, otherwise you don't have a circle. And remember that this is equal to r squared, so the radius is going to be the square root of whatever's on your right-hand side. Write the standard form of the equation of the circle with given center and radius. In this case, you're given the center point as 0, 0. Your center is HK. So what this means is that H equals 0 and K equals 0. And then you're being given R. R equals 9. So when we're writing the standard form equation of our circle, and I'm going to include the zeros and then simplify just so that you kind of get to understanding where these pieces come from. X minus h, so x minus 0, quantity squared, plus, we got that plus sign in here, y minus k squared equals r squared. And then we'll simplify. X squared plus y squared equals 81. And there's the equation for the circle with center 0, 0 and radius 9. All right, now we're going to do this again. Write the standard form of the equation of the circle with the given center and radius. This time, we're being given a value of h as -8 and k is +8 and r equals 5. So we're going to go back. Let me remind you of what our equation is. X minus h quantity squared plus y minus k quantity squared equals r squared. And you're just going to plug it in at this point. X minus -8. Now, if you want to go straight to x plus 8, that's fine. I just want you to see where this is coming from. Plus y minus 8 quantity squared equals 5 squared. And then we'll simplify. This is x plus 8 quantity squared plus y minus 8 quantity squared equals 25. And that is your standard form equation for the circle. Now that you know how to use that standard form equation of a circle with the radius and the center point, we will graph some circles here. Make sure we know how to graph these. Graph the equation and state its domain and range. Use interval notation. Note it's an equality and not an inequality. We'll start with the equation of the circle with the center on the origin. X squared plus y squared equals 64. This is a center of 0, 0. And you know that because you don't have x minus some number h squared plus y minus some number k squared. In this case, h and k have to be 0. And the radius is 8. That's because the radius squared is 64. So it must be the case that the radius is 8. Don't forget to take that square root. Now when you graph your circle, your center is at the origin. The radius is 8. So that means that what I usually do is go out 8 in all 4 directions. So to the right, and then go up 8, left 8, and down 8. And I get those 4 points for the edge of my circle. And then from there, I just do the best job I can, making it look like a circle and graph it, connecting these points. Usually it ends up looking sort of footballish, but do the best you can. That's not terrible. So that's how you graph x squared plus y squared equals 64. Now the next question is, on the same coordinate system, graph x minus 2 quantity squared plus y plus 3 quantity squared equals 25. So for this circle, we're looking at a center. And I'm going to remind you here, I'm going to put the equation up here at the top. X minus h squared plus y minus k squared equals r squared. The center is hk. H and k are whatever follow the minus sign. Now, clearly in this situation, h has to be 2. Swap them out. 2 is in the place of h. The x coordinate of the center is 2. But for the y coordinate, remember that y plus 3 is y minus negative 3. That means that k must be negative 3. So your center is at 2, negative 3. And then the radius squared is 25. That means the radius is 5. So we're going to graph this on the same coordinate grid, and you kind of get an idea here of what this system of equations would look like if it was all presented together. So your center is 2, negative 3. So 1, 2, and then down 1, 2, 3. There's your center. Now for your radius, you're going to go out 5 in every direction. So go out 5 to the right, which would get you up to 7. And 5 to the left. And 5 up. And 5 down. And then you will graph the circle. Just connect your points with some nice smooth arcs. Do the best you can. And that's it. That's your crash course on circles. It sort of gets you prepped also for what we're going to be doing in 2 more weeks with Chapter 7, conic sections. Now, we're going to graph nonlinear inequalities in 2 variables. So what we did at the beginning, but now instead of looking at linear equations, we're going to be talking about nonlinear equations, or inequalities, I should say. Follow the same process for graphing linear inequalities. The test point is now in a region rather than a half plane. So graph the inequality x squared plus y squared is greater than 49. All right, so we have a circle with the center at 0, 0, and the radius is 7. Now, bear in mind that you have a greater than symbol, not greater than or equal to. So when you graph your circle, try to be thinking in advance that you're going to have to graph your circle with a dotted or a dashed curve. All right, so your center is at 0, 0, and your radius is 7. So go out 7 in every direction. And then draw your circle with a dashed curve, like that. Mine looks a little funky over here. Do the best you can. All right, so the difference here is that when we use our test point, we're talking about regions. That means either we're going to shade the region inside the circle or outside of the circle. And in order to determine which one, we're still going to be using test points. So you may absolutely test the point 0, 0 if you'd like. It's such an easy point to test, and it's clearly inside the circle. The point that you wouldn't want to test would be something like 7, 0, because that's not clearly inside the circle or outside the circle. That's sitting on the boundary line. Don't test there. But you can test at 0, 0 because 0, 0 is clearly inside the circle, so it's in this region. So we'll say 0 squared plus 0 squared is greater than 49. Is that true? Well, no, because 0 is greater than 49 is false. So because the point 0, 0 did not make a true statement, we cannot graph the region that includes 0, 0. So we're gonna, let's not say graph, let's say shade. Shade the region not including 0, 0. So this is kind of weird to think about, I guess. Sometimes students find this whole inside outside of the circle thing weird, but any point inside the circle is not going to solve the inequality. I mean, you can test any point you'd like. If you prefer to test 2, 2, that one's clearly inside the circle, do that. I just chose 0, 0 because I thought it was the easiest to work with. But 2, 2 would clearly be wrong also, because then you'd have 2 squared plus 2 squared is 4 plus 4 is 8, which is not greater than 49. You decide. But when you're shading the region that does not include 0, 0, you are shading the region outside of the circle. So it should look like this. Yeah, just to make sure it looks clear what region's shaded, but usually that's not an issue. The next one is not a circle. It's actually a parabola. Thinking about this as y equals x squared shows you that this is your standard parabola. And you know how to graph that. It's got a point here at 0, 0. It's got a point at 1, 1. It's got a point at 2, 4. And then it's got that y-axis symmetry like that. It's also got a point at 3, 9. There's 9, there's 3. Gosh, these squares are so little I can barely see them. Okay. And again, we have a situation where you have a greater than symbol. It's not greater than or equal to. So when you draw your curve, you need to draw it with a dashed curve, not a solid curve. So I'm going to draw this parabola. Make sure you can tell that it's dashed or dotted. Now you need to pick a test point because you're going to either be shading the region inside the parabola or outside of the parabola. Don't pick 0, 0. 0, 0 is on the boundary line. It's not a good test point. Boundary line. Not a good test point. So maybe you could test something like 0, 5. 0, 5 is very clearly inside the parabola. If you don't want to use 5, you can just use something smaller like 0, 1, which is clearly in there. But I'm going to test 0, 5 because that's very, very obviously inside this parabola versus outside. So we're going to test 0, 5. I mean, if you wanted to also test outside of the parabola, you could always do 5, 0, then see what that yields, and then follow that. But I'll test 0, 5 to determine whether I need to shade inside the parabola or outside. So x equals 0, y equals 5. So I want to know, is 5 greater than 0 squared? Yes, 5 is greater than 0 squared. So I'm going to shade the region that includes the test point, and that's inside the parabola. Now, I know that you cannot shade the entire region. Of course you can't. It would just keep going up and up and up and up and up inside this parabola. Just shade whatever you have graphed. Do the best you can. Graph a system of inequalities. The solution set of a system of linear inequalities in two variables is the set of all ordered pairs that satisfy each inequality in the system. So now instead of just graphing one inequality and shading a region, we're going to be looking at a system of inequalities and determining which overlap we're going to take. Thus, to graph a system of inequalities in two variables, begin by graphing each individual inequality in the same rectangular coordinate system. Then find the region, if there is one, that's common to every graph in the system. This region of intersection gives a picture of the system solution set. All right, so let me show you how to do this. Now, I know that a lot of times it's easier to graph these lines when you use intercepts, but I think it's easier to look at the shading when you get them solved for y. All right. We'll do this two ways. Let's graph each line using the method of intercepts, because I think that's easier. All right, so to find the intercepts, to find the y-intercept, we'll let x equal 0. So if we let x equal 0, we'll just have negative y equals negative 2. Remember, for now, since we're just graphing the line, we're just going to use an equal sign. Don't worry about the inequality until you actually start with that shading. So negative y equals negative 2, so that means y equals 2. Great. That's your y-intercept. To find the x-intercept, let y equal 0. So if we let y equal 0, we just have 2x equals negative 2. And then divide both sides by 2, and you get x equals negative 1. So your x-intercept is at negative 1. Now, when you go to graph this inequality, notice that it has a less than or equal to sign. That means you can graph this with a solid line. So go ahead and connect these points with the solid line. And if I were you, I would label that graph, because you're going to have another graph here and you don't want to get them mixed up. So this one is going to be 2x minus y is less than or equal to negative 2. So we'll label that. All right, for the next inequality, this is my focus here. It's better. Okay. We're going to do the same thing. To find the y-intercept, we'll let x equal 0. So if x equals 0, we're going to end up with 2y equals 4 and y equals 2. So we already have this point here. No big deal there. And then to find the x-intercept, we'll let y equal 0. So if y equals 0, you'll have x equals 4. And then we'll put that point down here. Now the inequality for this line is strictly greater than. So since the inequality is strictly greater than, you're going to graph this using a dashed line. So we're going to connect these 2 points using a dashed line. I'm trying to make mine a little bit straighter here. Looks something like that. And then I'm going to label it. This is x plus 2y is greater than 4. Okay. Now, we're going to have to look at each one of these lines individually. My suggestion to you is to actually pull out these inequalities, starting with this one, and shade them based on their sign. I think that's going to be easier in this case than using a test point. This is what my suggestion would be anyway. So the first inequality is 2x minus y is less than or equal to negative 2. And again, this is just the original inequality that you were given here. To solve this for y, and you're going to have to do that if you're going to do this according to the sign, get y by itself. So move that 2x to the other side of the inequality. And then divide both sides of the inequality by -1. That means every term gets divided by -1. Now, the tricky part here is anytime you multiply or divide both sides of an inequality by a negative number, you have to switch the direction of the inequality. So when we divide this out, we end up with y is greater than or equal to positive 2x plus 2. Now, some of you might have preferred to start out doing this, and then you could have graphed this line using the slope and the y-intercept. So the y-intercept is 2, the slope is 2, so up 2 over 1. If you want to do that, that's fine. Totally up to you. But what I like about this is that once you solve for y, assuming that you did this correctly, y is greater than or equal to this function means that you're going to shade for all of the points that are greater than or equal to this value of y. That means you're shading on top of the line, not underneath. So the points that are greater than or equal to your function are all the points up here. Now don't shade too dark because you're going to have to shade for the other function also. But that's what we have so far. So I've shaded everything that is above this line. You could still use test points here if you prefer. Now what I need to do is do the same thing for the other inequality and then figure out the intersection of these two. So taking out the second inequality, just pull it off to the side over here. I have x plus 2y is greater than 4. We're going to get y by itself. So subtract x from both sides. And you get 2y is greater than negative x plus 4. And then divide each term of your inequality by 2. Now you're not dividing by a negative in this case. As long as you're not dividing by a negative number, you don't switch the direction of the inequality. So you have y is greater than negative 1/2 x plus 2. And again, you can check this and verify that the line is doing what it's supposed to do. The y-intercept is indeed at 2. The slope is negative. That means it's going down from left to right. That's what it should be doing. And your slope is negative 1/2. So down 1, right 2. Down 1, right 2. It's doing exactly what it's supposed to be doing. Now you can also then check your inequality symbol to figure out which place needs to be shaded on your graph. So this is saying that y is going to be greater than or equal to this function, negative 1/2 x plus 2. So you're going to shade all of the values of y that are greater than this line. So that means that you're shading above the line. So thinking back, you're talking about this particular inequality. You're going to shade above the line. And this time, I'll switch my direction of shading just so I can make sure it's clear. Okay, so I've shaded everything that's above this line, or you can think about it as being to the right in this case. Now, it looks like I have 3 regions shaded, but I don't. What you're looking for here is the overlap. Where did you shade in both cases? Now, we only have one region we only have the region shaded once here, I should say. It's only shaded this direction. Over here, we only have it shaded once. But up here, we shaded it both times in between these two functions. Right up here, we had it shaded both times. This is actually the solution set. Now, I don't want to get rid of the fact that we had a dotted line here. Well, there are all these tricky things going on. So I want to make sure that we represent that dotted line. But this is the solution, just this heavily shaded region. And when you're doing this on MyMathLab, you're going to graph one line, graph the next line, and there's going to be like a little paint bucket. You click on the one region you wanted painted. So let's say you were doing this on MyMathLab. you would click up in here and it would paint that region. Now, if you clicked over here, it would paint the region that just included the boundaries to the right of these graphs, right and above. All right, so if you were to graph over here, if you picked a point right there to drop your bucket, again, it would shade in this region. You don't want that. So make sure that if you were doing this in MyMathLab, that you would be clicking your paint bucket somewhere on here and it'll shade that region for you. Whatever you do, don't put the bucket on a boundary line. It gets very confused. I've had a lot of weird experience with that with MyMathLab. Okay, so that's how we shade a system of linear inequalities. Let's look at one that includes a nonlinear inequality. It's getting super dark in here. It's lamp time, which also means it's emulator time. Here we go. Wonderful. So this time we have a circle and we have a line. The circle is centered at 0, 0. And the radius is going to be 9. So when you graph your circle, and it has a less than or equal to, so feel free to graph it with a solid curve, centered at 0, 0, and then the radius is 9. So you're going to go out 9 in all 4 directions. And then make a nice solid curve. Okay. And now if you would like to use the test point method, this is the time when I would do that. So if you were kind of confused about what the heck did she do over here with using the direction of the sign, that's fine. Feel free to use a test point. Just if you're doing the test point method, graph one piece, then use the test point method, then graph the other function, and then use it again. So for instance, if you're looking at the circle and you're thinking, oh, I totally am thinking about using a test point of 0, 0, that's an awesome test point to use because it's clearly inside the circle. And you would test that point and you would say 0 squared plus 0 squared is less than or equal to 81. Check. That's true. 0 is less than or equal to 81. So you're going to shade the region that includes that point. I sometimes have students using a lot of different colors when they do their shading. They'll, shade for one graph using green and they'll shade for the other graph using purple. That's fine. I tend to discourage students from using red, but if you want to use green or purple or pink or orange, be my guest. I know on your exam that'll probably be helpful to you to see that. All right, so I'm shading inside the circle. What I tend to do, because I'm using pencil most of the time, is I just shade one of them like horizontally and the other one vertically. So I'll just do this one vertically inside the circle. Okay. Now, as far as my line is concerned, for this one, I'm going to use the method of intercepts to graph it. It's set up so beautifully to do so. To find the x-intercept, I'm going to let y equal 0. That means 5x equals 10 and x equals 2. X equals 2 is right there at this point on my graph. And then to find the y-intercept, I'm going to let x equal 0. That means 2y equals 10 and y equals 5. Y equals 5 is right here. And I can use a solid line to connect these two because I have a less than or equal to symbol. So I'm going to go ahead and make a nice line here connecting these 2 points. And I don't really feel the need to label these because clearly you can tell which one the circle is and which one the line is. Now we'll use a test point here too. I think that would probably be the best way to go. If you would like, you can rewrite this and solve it for y, but this one's set up so well to use a test point. And again, we can test the point 0, 0 because it's clearly to the left of this line, or if you want to think about it as being underneath the line. It's a good point to use. It's not sitting on the boundary. So we'll test the point 0, 0, and you'll get 0 plus 0 is less than or equal to 10. Check. That's true. 0 is less than or equal to 10. So we know that we will want to include that region in the graph. So when we shade, we're going to shade any region that lies to the left of this line, because that's the region that would include 0, 0. And here's where you're going to start picking up the overlap. So you know you shaded inside the circle and to the left of the line. The overlap happens when you're inside of the circle to the left of the line. So make that darker if you're using pencil. Make it very clear so that I can see the solution region. But it's there. It's that dark region right there. And I want to remind you again, if you're just like, okay, this is fun, but what the heck, why are we doing this? What you're finding here is that you can choose any ordered pair that's somewhere in here. Like for instance, 0, 0, or even the point -5, 0, or -1, -1, -1, -5, something like that. Any of the ordered pairs that lie in this very darkly shaded region are going to satisfy both of the inequalities here. They're going to satisfy that system of inequalities. And that's what you're looking for here. So it's not that you're looking for one point that's the solution. You're not trying to solve the equations or the system of equations. If you were, you'd be looking for the intersection points. You're trying to solve a system of inequalities. That means you're just looking for ordered pair solutions that work for both of these inequalities. And those solutions can be found inside the super dark region. If you were to choose a point here, for instance, inside the circle, but to the right of the line, well, that would satisfy the first inequality, but not the second. So if you tried to use the ordered pair 8, 0, well, great, that would work here, but it wouldn't work over here. If you tried to choose a point like -11, 0, well, that's great. That would solve the second inequality, but it wouldn't solve the first. You have to choose a point inside this darkly shaded region in order to satisfy both inequalities. Okay, now the types of problems you're going to see here as far as applications are concerned have to do with just these mathematical models of setting up these, I don't know, real life situations. Usually you end up in places where your variables, for instance, have to be positive, and they follow a certain set of criteria. Now, we're unfortunately not supposed to be covering linear programming in here, and I wish we would because it's so fun, but it's not required for the class, and we certainly don't have time to do things that are optional. So we won't get to linear programming. Unless, if you're really interested in this, feel free to look into the section. I think it's 5.6. I think it's 5.6. But this is all we'll do for 5.5, just setting up these systems here. Number 9, a person with no more than $1,000 to invest plans to place the money in 2 investments, telecommunications and pharmaceuticals. The telecommunications investment is said to be no more than 2 times the pharmaceuticals investment. That's important there. Telecommunications investment is said to be no more than 2 times the pharmaceuticals investment. Write a system of inequalities to describe the situation. X will be the amount invested in telecommunications, and Y will be the amount invested in pharmaceuticals, and then we'll graph the solution. Okay, so we have a few different things going on here. And again, you reread the problem to see if you can interpret any of this mathematically. First of all, a person with no more than $1,000 to invest. That means that X, the amount invested in telecommunications, plus Y, the amount invested in pharmaceuticals, has to be less than or equal to 1,000 because they have no more than $1,000. So this part right here means that the amount invested in telecommunications and pharmaceuticals has to be less than or equal to 1,000. It looks like you only have 2 of these multiple choices that give you that as an option. And by the way, if you're wondering, well, why can't it be an equal sign like B and C? Well, it didn't say that they were investing 1,000. It said that they had no more than 1,000 to invest. That means they could invest less than 1,000. So B and C are out the window. So if you're looking for keywords here, no more than means less than or equal to. The telecommunications investment, which we know is X. I'm going to start writing this down here. The telecommunications investment, which is X, is said to be no more than, which means less than or equal to, 2 times the pharmaceuticals investment. So X is less than or equal to 2Y. Well, that means that A is out. It's got to be D. All right, so when you're thinking about, I guess A was just kind of like, do you understand what each variable is representing? But the telecommunications investment, X, is no more than, less than or equal to, 2 times the pharmaceuticals investment. That's 2Y. Now, the X is greater than 0, and greater than or equal to 0, and the Y is greater than or equal to 0 just means that you cannot be investing an amount of money that's negative. It doesn't make any sense. If you're investing money in something, it's got to be some sort of value that's technically, it could be 0, but it also could be greater than 0. And that's where those 2 inequalities come from. So that's an example of how to read these. We'll do one more. Oh, wait, we forgot to graph. Yikes. Okay. X plus Y is less than or equal to 1,000. Here, we're going to use those intercepts. And this is going to be a little bit tricky, actually, because if we were using our intercepts, we would need this to be 1,000, not 200. Do we want to switch it out? Yes. So the maximum on your graph is given to as 200. But let's switch this to 1,000. And we'll do that here too. Are there the same number of ticks? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 20. Probably 2, 4, 6, 8, 10, 12, 14, 16. Okay, 20. Excellent. So we'll make that 1,000. And we know that X plus Y is less than or equal to 1,000. So let's use the intercepts method. We'll find the y-intercept by letting x equals 0. So that means y equals 1,000. And to find the x-intercept, let y equal 0. If y is 0, cover it up, then x would be equal to 1,000. We have this situation going on. And it's less than or equal to. Thank goodness, because I already graphed it as a solid inequality. Okay, so there's that one. Now we have x is less than or equal to 2y. If you find this confusing, just solve it for y. First of all, switch it around so it's written from left to right. If you bring the 2y to the other side, you're going to have to flip the inequality. The greater than side is already facing the 2. It should stay with it. And then y is less than or equal to 1/2 x. So when you're graphing this, and we have an equal to, so we can graph this using a solid line, you're just using a y-intercept of 0, because really technically it's plus 0. And then you're going up 1, right 2, up 1, right 2. So you're just following this slope as you make your way through the coordinate grid. Starting to lose these dots. They're so faint. Something like that. And this will be x is less than or equal to 2y. Now, technically, your line extends down further. And then you have x and y both being greater than or equal to 0. Oh, and we forgot to do our shading too. It's a very important piece of the puzzle, isn't it? I wouldn't use a test point of 0, 0 because it lies on this line. I guess you could if you're only thinking about it in terms of the first inequality, but I wouldn't use it for the second inequality. So let's use the test point 0, 0 for this first inequality. And then you'll get 0 plus 0 is less than or equal to 1,000. Yes, well, I mean, that makes sense because you have to choose a value that's underneath there. So when you're shading your inequalities, or when you're shading here, we're going to shade underneath this line because that includes the point 0, 0. However, because we know that x and y have to be greater than 0, you don't actually have to shade everything underneath and to the left of this line. You only have to shade the values for which x and y are positive. And then let's look at this inequality right here and pick a value that you want to test. So I don't know. I might choose something like a point down here and not something on the line, but maybe something really close to the line just to make it easy on us. So maybe we'll let x be 500 and just let y be 1, because you know it's somewhere in the shaded region in that case. And that's just a totally random point that I picked. You don't have to test that point. I just thought it'd be a good one to test. And we're going back down to this inequality. If x is 500, that's less than or equal to 2 times 1. No, 500 is not less than or equal to 2. So we don't want to shade the region that includes the point 500, 1. We're going to shade the other region. So that would be this region over here. And you can go ahead and make it super solid if you want to, just because you know this has to be the solution region. Now, technically, I could have gone and shaded everything that was above this line, but we already have an idea of where everything else is. So we know that this is our solution region. So whatever this person is investing, it's going to have to be the amount of money for X was, let's see, the investment for telecommunications. Somewhere the X value would have to be in this region, and the Y value would have to be in here also. So that would be the solution set for this set of inequalities. So that means that they couldn't meet this criteria and invest an amount of money that came from this region, because otherwise they would not be satisfying the second inequality. We'll do one more, or we'll have to do a little bit more of the work on our own. Number 10, the equation that represents the proper traffic control and emergency vehicle response availability in a small city is 2p plus 3f is less than or equal to 23, where p is the number of police cars on active duty, and f is the number of fire trucks that have left the firehouse in response to a call. All right, so don't lose those. I'm actually going to highlight them so I don't lose them. P is the number of police cars on active duty. F is the number of fire trucks that have left the firehouse. In order to comply with staffing limitations, the equation 2p plus f is less than or equal to 17 is appropriate. The number of police cars on active duty and the number of fire trucks that have left the firehouse in response to a call cannot be negative, so it must be the case that p is greater than or equal to 0 and f is greater than or equal to 0. Graph the region satisfying all the availability and staffing requirements using the horizontal axis for P, that's already labeled, and the vertical axis for F, again, is already labeled. We'll do that first, and then we'll answer the question, the last question that's involved here. Okay, so we have two things. 2p plus 3f is less than or equal to 23. We also have 2p plus f is less than or equal to 17. So we're going to graph each of these lines, and then we'll shade the region that satisfies each inequality. And you can still use intercepts. If we let p equals 0, we can find the f-intercept. So we're going to let p equal 0, and that gives us 3f equals 23. And then f equals 23 thirds. That's 7 2/3. So you can still graph this. It's just not going to be the most beautiful thing ever. And remember, this is your f-intercept, not y, but it's on the y-axis. So it's very important that we pay attention to that. So we'll graph an intercept at 7 2/3. So 2/3 of the way between 7 and 8 on the f-axis, which is the vertical axis. And we'll do the same thing here to find the p-intercept. We'll let f equal 0. We have 2p equals 23. P equals 23 halves. That's 11 1/2. So let's see. That's our p-intercept. 11 1/2 is just about right there. If we let this guy be 12. This is a less than or equal to, so we can go ahead and connect these with a nice solid line. And we'll label it because we don't want to get confused here. So this was 2p plus 3f is less than or equal to 23. So 2p plus 3f, I guess we could say equals 23 because that's the line that we graphed. And you're going to need to do some shading. If you want to do a test point now, it's probably a good idea. You've got a region that includes 0, 0, and you've got a region that doesn't. So I'm going to say let's test 0, 0. And this one's going to be super obvious when you test it. 0 plus 0 is less than or equal to 23. That's true. So that means you're shading underneath the line. Now you were already told that f and p have to both be positive. So that means you don't need to worry about shading to the left of the y-axis or the f-axis or underneath the p-axis. So we're just going to shade below here. And then we'll work on our second inequality. Let p equals 0 to get the f-intercept. When p equals 0, you have f equals 17. Well, we're going to have a hard time graphing that one because it's really high up here, but we'll do the best we can. You can always, by the way, well, even if we rewrote this into y equals mx plus b, we'd still have a y-intercept of 17. So let's expand this out a little bit. 11, 12, 13, 14, 15, 16, 17. Approximately. Do the best we can. Clearly didn't think that one through, did I? All right, so there's that. And then we'll let f equals 0. If f equals 0, we have 2p equals 17 and p equals 17 halves. 17 halves, so that's 8 1/2. 8 1/2. It's right down there. So go ahead and connect these two points with a nice solid line. And we'll label it. That is the line 2p plus f equals 17. Isn't this so fun? I really enjoy this. I really do. Okay. Now we'll look at this inequality. And again, very clearly, 0, 0 lies to the left of this region. And it's clearly not on this side of the line. So it's a really good point to test. So we're looking back, 0 plus 0 is less than or equal to 17. Yes, that's true. So we're going to shade to the left of this line, or if you want to think about it as being underneath, that's fine too. And then you're looking at the overlap. Well, the place where we had both of these regions shaded was in this lower left corner. I even have sometimes students will make their lines, their border lines extra bold like this, so it's clear to see it. If you want to do that, that's fine too. Everybody's got their own thing. Some students are very artistic and they make this look just gorgeous. But that's your solution region. Okay, now we have one more question to answer. If 6 police cars are on active duty and 4 fire trucks have left the firehouse in response to a call, are all of the requirements satisfied? Well, 6 police cars, that's P. So if P equals 6, and the number of fire trucks, F, is 4, have we satisfied the requirements? Well, look at your graph and see if you can answer this easily. If P equals 6, right here, and F equals 4, what do you think? If you eyeball it, does it look like it? It's really hard to say. It looks like a close call. P is 6, F is 4. I'm thinking that point looks like it's right about there, but it's so close to that borderline. I think we're going to have to check it. Let's check it. So we'll do a test point. Similar to what we did here, we'll just do it twice. We'll let P be 6 and F be 4. So let's say, let's test 6, 4. And then we'll do it twice. So 2P plus 3F is less than or equal to 23. 2 times 6 plus 3 times 4 less than or equal to 23. Technically, I don't need the question mark there. So that's 12 plus 12. Is that less than or equal to 23? Well, 12 plus 12 is 24, which is not less than or equal to 23. So you don't even have to bother testing the other one because you tested the first inequality and it didn't work. So it must be the case. And by the way, that was this line. It does not satisfy this inequality. So don't even worry about the other one. It doesn't satisfy the system. So the answer to the question is no. So we'll say then no, the requirements are not satisfied. So that's just sort of a very contrived application. I know it seems a little bit silly, but really there are a lot of real life applications that you can solve with systems of inequalities. All right, the last thing I want to do here for today is introduce you to these matrices. We're not going to do a whole lot with them today. The bulk of what we're going to do in 6.1, we're going to do next time. I just want to give you an introduction as to what these things are going to look like. Okay, chapter 6, by the way, we're still going to be working on solving systems of equations, but this time we're going to be focusing more on bigger systems of equations where maybe we have 3 equations and 3 unknowns, sometimes 4 equations and 4 unknowns, maybe even 5, who knows. But we'll see. Well, we're going to be doing all of these with matrices. And if you've never used matrices before, well, you're going to be doing it a lot in chapter 6. We're going to be doing it all the time. So let's start. Matrices are used to display information and to solve systems of linear equations. I'm also going to be showing you how to use these matrices in your calculator next time. So I'll be doing a lot with your calculator here. A matrix, now the plural of matrix would be matrices. You don't say matrices, you say matrices. Also, you get so used to saying matrices that sometimes I hear students say, well, this matrice has this, or this matrice has that. No, if it's one, it's a matrix. If there's more than one, they're matrices. Anyway, a matrix is a rectangular array. The information is arranged in rows and columns and placed in brackets. The values inside the brackets are called elements of the matrix. So what we're going to do is write augmented matrices for systems of linear equations. All right, so we're going to write an augmented matrix. This has a vertical bar separating the columns of the matrix into two groups. The coefficients of the variables are placed to the left of the line, and the constants are placed to the right. If any variable is missing, its coefficient is 0. This is very straightforward. You will not have a problem doing this. Very, very straightforward thing to do. Okay. So starting out here with our augmented matrices, you are going to draw some brackets. So if you've never used matrices in your life, this is your first time. Yay. You're going to take the coefficients and first take notes of what type of variables you're looking at. X, Y, Z, X, Y, Z, Y, and Z. So you know that you just have to represent 3 variables. So take your coefficients out. X, Y, Z. So 3x plus 2y minus 9z. Make sure that the -1 gets a negative coefficient. Do the same thing for the following 2 rows. So x gets a coefficient of 1, y gets a coefficient of 3, and z gets the coefficient 4. And the last row, you don't see the variable x. Represent that with a 0. 0x, 3y, -8z. Now notice I drew a vertical line here. I did not draw the other side of the bracket. That's because the other side of the bracket comes after the vertical line. On this side of the vertical line, I'm going to draw the constants that are on the right-hand side. So we're equal to 15, 22, and 27. That's it. That's how you take a system of linear equations and turn it into a matrix, an augmented matrix. Okay, so you need the two parts here. You need the brackets, but you need the coefficients in front of the variables, and then on the right-hand side of your vertical line, the constants. So super straightforward. Write the augmented matrix for the system of equations. And this might be a place where you want to pause the video and stop, do it yourself, and make sure you did it correctly. Now this time you have an x, a y, and a z. In the first equation, you just have x and z. So you have 7x, 0y, and 3z. In the second equation, you have 0x, 5y, 3z. And in the last equation, 4x, 3y, 2z. And on the right-hand side, you have these coefficients, 39, 2, and 25. Now we're going to work our way backwards. Write the system of linear equations represented by the augmented matrix. Use x, y, and z, and if necessary, w. Well, if you had 4 columns here, then you would use w. By the way, I feel like maybe now is a good time to discuss the difference between a row and a column. In case we're not sure, columns go up and down. So this is a column, 704. A row goes across. So we're going to go backwards and we're going to write the system of equations represented by the augmented matrix. But I only see 3 columns. That means I only need 3 variables. So looking at your first row, 9x plus 5y plus 9z equals -2. Second row, 8x plus 8z equals 4. You don't need to write a plus 0y. feel free, but you don't have to. And I actually don't think my math lab will want you to. 7x plus 4y equals 2. And you don't have to leave the spaces. I only did that just so that you could tell that there would have been something there, but we're not forgetting about the zeros. And that's how we turned an augmented matrix into a system of linear equations. And if you're wondering, why the heck are we talking about this at all? Well, we're really going to get into that a little bit later, but we're going to start talking about the idea of row operations next time. I'll talk about it slightly right now, just to sort of plant the seeds. Okay. A matrix with ones shown on the main diagonal. Now, the main diagonal is just this diagonal that starts in the upper left corner and moves down and to the right. So this is your main diagonal. A matrix with ones shown on the main diagonal and zeros below the ones, 0, 0, 0, is said to be in row echelon form. Now, we use row operations on the augmented matrix to produce a matrix in row echelon form. So a lot of times you're not going to be lucky enough to get this form. And if you're like, okay, who cares? Why does this form matter? Well, I'm about to show you why. If we have a matrix in row echelon form, what we can do is we can work our way backwards using back substitution to find a solution to the system of equations. I mean, think about what this means. Look at this. Look. 2x, I'm looking at the 2. Sorry. 1x plus 2y minus 5z equals negative 19. Now we just have y plus 3z equals 9. Z equals 4. When we have ones on the main diagonal and zeros below it, this allows us to back substitute using that one solution that we do have. So I have z equals 4. Great. Well, now guess what? I can work my way backwards. I can now find y because I know that z is 4. So I know that y plus 3 times 4 equals 9. Substituting in that value for z. So y plus 12 is 9. And y equals, well, 9 minus 12 is negative 3. So now I know z and y. And as long as I know both of those values, then I can go over to my first equation and solve for x. Now, if you want, you can solve for x by just moving everything to the other side. You might find that to be most helpful. So move the 2y over and move the 5z over. And you get x equals negative 2y plus 5z minus 19, just by subtracting 2y from both sides and adding 5z to both sides. You might find that helpful. Let me see, I don't want this to look confusing now. Okay, now, negative 2y is negative 2 times negative 3. Remember, we found that value for y. Plus 5z means plus 5 times 4 minus 19. That means x equals 6 plus 20 minus 19. 20 minus 19 is 1. 6 plus 1 is 7. Well, there's the solution to your system of equations. Isn't that amazing? But then you might be wondering, okay, well, that we got lucky that time. We just had this situation where the matrix was in row echelon form. You didn't really get lucky. Somebody worked to get that matrix into that form. It originally probably didn't look like that. I say all this to let you know that what we're going to be working for in 6-1 is we want to get to a point where we can take a matrix that looks like this and turn it into a matrix that looks like that. And we're going to be doing that using row operations. And I'm going to be talking about row operations on Wednesday. Now, Wednesday is when we really get into the thick of this 6.1 material. We're going to be doing a lot of row operations. We're going to be getting matrices into row echelon form. back substituting to find solutions. So be prepared for that on Wednesday. Make sure that you are ready to go. I'm going to put up some homework just to get you started, get your feet wet here, and plant the seeds so that next time you can be ready to work on these row operations. Okay, if you have questions, email me. And please let me know what you thought. And I know sometimes students don't want to have their information out there because if you want to say something critical, then you don't want me to know that it was you. I understand. I'll probably send out a Google form just saying, what did you think of the video? Was it basically just like sitting in class? Or did you find that it was better? Or was it worse because you couldn't ask questions? I know you guys don't usually ask a ton of questions, but there's usually stuff here and there. So let me know what you think. Email me if you have questions. And if you do have a question about something that we did on the worksheet, just let me know, like, hey, on, 6.1, when you did that problem where number 3, I don't understand how you did this, or I don't understand how you did that. So make sure that you're being descriptive so that I understand what it is that you have a question about. But I'll put up some homework so you can get ready. And that is all. I'll see you. Well, I'll email you, but I'll be here for the office hour Wednesday, and I got to get off here right now because I got to get out for your office hour today. And I have to finish your quiz. But enjoy. And I'll be in touch via email.